Hello, linear algebra student. This video is for chapter 3.1, part 1. We're going to talk about introduction to determinant. Determinant is a number that you can calculate from a matrix. So basically, if someone gives you a matrix, which is n times n, you can calculate a number called determinant. You recall that we talked about determinants in chapter 2 when we're dealing with constructing inverse of a 2 by 2 matrix. Namely, if I have a matrix of entries A, B, C, D, a 2 by 2 matrix of A, B, C, D, then the determinant is AD minus the other diagonal BC. And in the process of calculating the inverse, this is used because the inverse is 1 over the determinant of it with the entry, swapping the diagonal entry and then doing the opposite of the off diagonal. So in the first part of this video, we'll talk about how to find determinant of any matrix. Do we do diagonal multiplication like that? For 3 by 3, it's more complicated than that. So let's consider a 3 by 3 matrix that has like the normal naming convention, A11, A12, A13, A21, A22, A23, A31, A32, A33. So that's the normal one. Oh, by the way, why do we need to learn determinant? In 2 by 2, we need it when we are constructing inverse, right? Now that we know how to do inverse by elementary row operation, so what is it useful for? It's actually by itself, determinant is useful in calculus. When we do Jacobian later on, when you do calculus 3, you will run into something called a Jacobian matrix, and the determinant of the Jacobian is important. It can be used to solve systems of equation by itself, actually. Other than elementary row operation, determinant can be used to solve systems of equation. We'll learn this in 3.3. So let's get back to how to find the determinant of a 3 by 3 matrix, and maybe it will let us glimpse into how to find the determinant of n times n matrix. So first of all, we want to do an elementary row operation to clear this. If I clear this zeros, I would multiply, I will scale the second and the third row by A11 first, or A11, and then I'll multiply I'll clear this by subtracting A11, A21 by A11, A21. So basically, I would need to scale A1, multiply R1 by A21 because I want to get it to 0, and then subtract the whole row with R2 and put it back to R2. So this elementary row operation will result in 0 in the first entry of row 2, and would have A11, A22 minus A12, A21, because that's exactly how this entry would look like if we want to subtract this. And the same idea would goes for A31. If I multiply A31 here and negative A31 for row 1 and add to row 3, I will have the 0 entry, and every single one of these will become the original entry minus the A12, A31. Okay, A12 times A31 because I multiply this by A31. So that's the idea. And we say that this original matrix is row equivalent to this matrix. And the second thing would be to get rid of this entry. And you can see by algebra that if you have to clear this, so we will multiply the original of this entry to this, and then subtract or add the two row together and put it into row 3. So all along, this would become, the row 3 would become 2, 0, and a entry called A11 times a delta. So this delta is what these two multiplies together, basically, right? There's this one and this one multiplied together. And so we have all a big entry like this. Because if A is invertible, then delta or this expression delta must not be 0. And then this value would become the determinant of a 3 by 3 matrix. Okay. Because if it is 0, then this become a 0 row and would not be invertible. Right? So we can actually group this together by pairing up, they have 3 entry and 3 subtract entry, group them together, and you'll see that if I can factor out A11, and then the rest of them will become a determinant of A11, capital A11. So this is called a submatrix. And then A12 is the determinant of A12, A13 times determinant of A13. What is A11? A big A11 are the submatrix obtained by deleting the first row and the first column are in the original matrix. So you can see that we can now obtain the recursive definition of a determinant. What it is to find a determinant of A, we will just use one row, A11 times determinant of capital A11, which is a submatrix, deleting the first row and the first column, minus A12, and then the determinant of the submatrix A12, which is found by deleting row 1 and second column, until A1n, and then the submatrix deleting the first row and the nth column. And we can actually write it as a sigma notation. And you can see that this add and subtract, if we want to make it nicer, and the way we figure out what entries we want to do, or if it is a subtract or positive, is we introduce something called a cofactor. The cofactor is the number aj, which is -1 times to the power I plus j and the determinant of aij, and we call it the cofactor of ij. So then the determinant of a would become, we don't have to do the plus and minus, we just have to say A11, C11, A12, C12. So this is known as the cofactor expansion across the first row of A. And we have this theorem that generalizes it. You can actually expand it across the ith row. It doesn't have to be the first row. And in order to find the cofactor sign, we can also use a checkerboard like this, because basically the plus and minus change whenever I and j change by 1. So if you want to find, if you want to determine if you have a positive or negative in the cofactor notation, you can use this checkerboard of sign. So let's actually use it. The first one is to find the determinant of a 2 by 2 matrix. I don't think I want to use a cofactor, but yeah, for the sake of it, maybe, no, I don't think I want to do it, because we do have a formula. So just redo the formula. So we say determinant of A would equal to 2 times 2 minus, remember it's minus, the off diagonal. So it would be 4 plus 15. So it's equal to 19. And it's not 0, so it is invertible. So one very important features of the determinant is if it is not 0, it's invertible. If it's equal to 0, it's singular. So let's do the expansion for this. Let's try the first row first, right? Use the expansion for the first row. So we will say determinant of A would equal to 1 multiplied by the determinant of, if I delete row 1 and column 1, row 1 and column 1, I have 6, negative 1, 5, 0. And then I want to subtract, so I'm going to expand for row 1. Subtract 4, delete first row and second column, it will be 3, 0, negative 1, 0. You have a smaller matrix, and then I expand 0 plus 0 but 0 is nothing. So we just, for the sake of, we usually don't write it, but you can see that I expand across the first row by deleting each column and have a smaller submatrix like this. So this would be 1. This is a 2 by 2. I can do it. 0 minus -5. And then minus 4. This would be 0 minus 0. And then plus 0. 15 minus 0. So, but all this 2 is all 0. So it is 5. So because it's 5, it's not 0. So I know that A is invertible. Let's look at another one. So in this one, I'm going to not expand on the first row because I have 3 entries, right? But in the first column, I can actually expand in column. I'm going to do column. So because there's a 0 here. So I would say 5. I delete first row, first column. 3, -3, -4, 7. Minus and a plus, right? So it become a plus 2. I don't need to expand this, so this is a plus, this is a minus, this is a plus. And I delete this 2, so be -2, 2, 3, -3. It's easier when you're, getting a submatrix by deleting the corner row. When it is in the middle, it's kind of harder. So we'll do this in the next one. So this will be 5, 21 plus 12, right? Plus 2, 6 minus 6. 6 minus, so this has become 0. So it'll be 5 times 33. That is, oh, this is a minus, right? Yeah. So actually it's not 33. 5 times 9. So it is 45. It is 2, yeah, 2 negative become a positive. I am doing a minus. So let's do the next one, which is a 4 by 4. So the power of the recursive is you would do one lower than the other. So let's see which row is or column is good. So I'm going to do this row because I only have one entry to do, right? So I will use row 2 and I'll expand it by deleting this and this. So imagine if this is off and this is off, I would have 1, -2, 2. This is off, so 2, -4, 5, and then 2, 0, 5. Right? And then I don't have to do any of those. Now for this one, maybe I'll expand from the last one. 3, 2, -2, 2, -4, 5. So this is a plus, minus, plus. Okay, so and then when I plus, minus, plus, so it's still a plus. Expand this. So 1, -2, 2, -4. Right? So that would equal to 3 times 2 times what it got, -10 plus 8. Oh, -10 plus -10 -10 plus 8 plus 5 -4 plus 4, right? This becomes 0, so I end up actually having 3 times 2 times -2. So that is 12. Is this 3 a -3? Let me see. Oh, I think I forgot. Plus, minus. Yeah, this is a -3. I am off. I forgot. So that is 12. This is the answer.